Okay, so today we'll talk about sort of generation expansion. Basically, what happens if you need to build more generators or build more transmission lines? How do you think about this? Right, so this will not be on the final because you won't have a chance to do a homework on this. And most things here actually for not require some finance knowledge that I don't assume in this class. So basically take a look at these two concepts. And this has become interesting because finally there's actually a bunch of money to build generators. So if you look at the Inflation Reduction Act and the sort of the Infrastructure Act from the federal government, there's not sort of insignificant amount of money there to build new things. So now it's a question of suddenly sort of the finance or return look a lot better. So we're going to look at how to think about these problems, both building generation and building lines. So before I go into detail here, any question about the last homework? Right, so whatever is on that homework could be on the final exam. Okay, so final exam will come out tomorrow before 5 p.m. I'm finishing making it, so if I make it before then. Will come out tomorrow before 5, and we'll be doing Friday at midnight, basically. Okay. Any questions about that? Okay, so tomorrow, of course, not tomorrow, but Friday's class will be office hour where I can answer questions about the final. Again, that's for you to have a look at the final before coming. But it's not a chance to sit here and for 2 hours and do the final and ask while you have questions, right? That's really not the point. Okay, so the idea is definitely take a look before asking questions. That being said, if you have any questions, please do ask. Okay, so this class we don't have a TA. So normally the TA checks the problem to make sure they all make sense. This time I'm making it, there's no guarantee that all the numbers work. Okay, there could very well be I make a question that the numbers don't make any sense. Okay, so if there are problems, do let me know. But the idea is for you to take a look at least before Friday afternoon. Right. Okay, so the no questions there. Let's look at the generation expansion. The generation expansion and the transmission line expansion are sort of they're unique topics because it takes so much money to build these things. These are very capital intensive sort of investment you have to make. So let's say, I'll say example, if you are now today going to build a new nuclear plant, let's say a reasonable sized nuclear plant, say 2 gigawatt, how much is it? Okay, so let's say you want to build this new power plant, you go to investors, you want to say, I want some money, to go in and build this plant. How much money do you think you need to get? It's just building the plant. We're not counting the fuel costs and things like that. It's just, building this thing somewhere. And assuming you already have transmission infrastructure to that place. So all you need to do is build a new plant. And the transmission already there. Any idea of the ballpark of the cost? So this is around $5-6 billion at least, depending where you are in the country, right? So, if you're in California, depending on where you want to build it, building 10 gigawatt of generation can easily run you tens of billions of dollars for that, right? So all these are very capital incentive. And it used to be the way you build this sort of capital incentive things, the government builds it, right? So you pay taxes to build this and just cost however much you build it, then you just get taxes and that pays for the plant. So today the thing is right, there's no longer monopoly. So there's a market. Nobody has to buy power from your plant. So you actually have to compute the rate of return and see if that makes sense. Okay. And you always need to think about sort of new technology that may come in. right? So if you start building coal power plants 20 years ago, that's not a great investment. Right? So you build this kind of things, you think this will operate for 40, 50 years. Coal 20 years ago seemed fine. You can make money from that. Today, most coal power plants don't make any money. The most power plant retirement comes from coal power plants. And not because necessarily for stability reasons, but more from economically, you cannot compete with other things. Okay? So you have to think about these things, right? So this again, to actually do this is extremely complicated. You're talking about billions of dollars. You have an army of people doing this kind of calculations. So we're going to see sort of examples how this is done. And consumers, basically from a consumer's perspective, deregulation is good in the sense that you don't have to buy from an expensive power plant. It can be challenging because as consumers, you need somebody to build power plants for you. Right? You need somebody to undertake this very expensive capital projects. You need somebody to build the things that'll take for 40, 50 years to make their return back. Okay, so sometimes you have to give some extra incentive for people to build. You cannot wait until people sort of believe they can make money and spend sort of huge amount of capital to build power plants. Often what the government does is sort of give you extra incentives just if you start building. We'll guarantee you some rate of return. Maybe not everything, but you'll be guaranteed some amount of money to start building. Okay, so as competition has a benefit of that, you don't have to buy from the any particular power plant. As a drawback of it could be that nobody wants to build any. And sometimes we're seeing this can be an issue in some areas where everybody's hesitant. You don't know when your technology is coming online. So you don't want to build anything, right? You want to sit and wait. Then that can create problems for 10, 15 years down the line. You run out of capacity, but takes multiple years to build power plants. Okay? So you do see incentives given to the generator to build this. So we're going to look at from sort of investor's perspective is what kind of numbers goes into the computing, for example, how much money you can make. Okay? So the way this numbers break up is you normally look at things that matters for a plant. As for a kilowatt, how much money, so this is the capital cost you have to put in. You look at how long do you expect this plant to last. Okay, so you're not going to make your money back in a few years. You're counting on this plant being in the system for multiple years, for a number of years. So 30 years is a typical number to enter here. Heat rate, I rated output. So what does this mean? Just given the units, what does this mean? What does heat rate mean? For example, what kind of plant is this? Right, so this is either gas or coal. This is a thermal power plant. So what does this mean? Right, right. So that's exactly right. This is the amount of heat, right? So when you compute fuel, things like gas or coal, how do you quantify how much coal do you have, or how much gas do you have? You normally look at the sort of the heat stored in this much. So you say this is how much BTU. So it takes you this much BTU to generate 1 kilowatt hour. So that's probably a coal power plant. Then, so this you can compute. This depends on technology. This is not very difficult to compute. When you build a power plant, you know the technology you have. So coal has a certain sort of heat rate. Gas has a certain heat rate. Something like combined cycle has a much better heat rate. Anyways, this depends on the exact technology you have. The more challenging part is this number, your cost of fuel. This depends on the market, right? So if you're coal, you're slightly less volatile. If you're gas, this could be a number that goes up and down, be quite volatile what this number is. So you look at the gas price For example, even right now in the United States, it goes up and down by a factor of 2 every several months. It's not a very stable price, right? But when you build a plan, you have to factor that in, right? So you have to factor that into it. So you can ask, is it worthwhile to build a 500 megawatt plant? Right? And does it make sense given all these numbers to build that plant? And so you have to assume a utilization factor of this as 80%. This says basically your plant is on 80% of the time. So what is your plant doing the other 20% of the time? Right? So if you're wind or solar, this number is not great, right? Because sometimes you have no power. If you're wind plant, utilization factor sometimes is 40% just because you don't hit your capacity. But here you're a thermal generator. So what do you do the rest of the 20% of the time? Why are you not on, say, 95% of the time? What happens? Like, well, if you build, I mean, there's no uncertainty essentially with this plan. Where does this 20% go? Sorry? In No, that's compared very small. Right? So 500 megawatt plant, the internal machinery that's not even close to it. Okay. But reserve, you still make some money, right? So this utilization factor is basically you take everything, you multiply by 0.8. That 0.2 is assuming that your plant doesn't exist for that 20% of the time. There are two reasons. One is a technical reason. The other is from a market reason. So for the technically, why might a plant not offer it 100% of the time? Yeah. Right. So one is you have to do maintenance, right? So you plan, most generators cannot offer it for a couple of months, keep operating for a couple of months. So your hydro, you may be able to do that, but for thermal plants, you do some maintenance. So part of this is maintenance, but that's not all of it, right? You don't do maintenance 20% of the time. Where does some of the other things come from? Think of the market reason. Why might you not be making money for some fraction of the time? What can happen if you're in your market? Related. So we learned this term. Yeah. So what can happen is you could be more costly than the marginal generator. The market may not dispatch you in that sense. Okay, right. So that's why you have a market, right? I built this power plant. So if you do this in a monopoly, you basically this doesn't change. You have a utilization factor. You're not on 100% of the time, but you're on much more than 80% of the time. So what this happens is you may not be dispatched in the market, depending on how you're bid. You have to bid in the market. So you have to allow for a factor that you're not clear. Okay, the market doesn't clear you, right? So you extra marginal. So okay, so you have to sort of make allowances for both. You're doing your own maintenance, and if you don't bid, if you bid or the load is very low, or that day happens to have a lot of wind, it may not be clear. So you come up with this number, think of how often you're on in the market. And then of course you have to assume, so if you're operating, how much money do you get for generating electricity? Okay, so all of these are numbers. So this number, this number, this number has a lot of work behind this. Right? Again, so if you are actually building nuclear power plants, I think recently somebody spent maybe $12 billion or something building some, investing in nuclear power plants in the US. So again, you have a lot of people computing these numbers. Okay, you go in and you compute these numbers. All right. So here I would just say somehow we compute these numbers. Then what you do is you compute all your costs. You compute your investment cost, you compute your production, how much energy can you make, your cost as that production, and your revenue, and then you look at, is it worth your while to do this. And so investment cost is, this is dollar per kilowatt. This is the how much, this is the capital cost of building the building or the machinery for the plant, a 500 megawatt plant, and this is $500 million something dollars. Right, so this is not a typical number. So you can scale this thing by the size of the power plant. You can see, so just capital-wise, capital cost of how much this is. Again, what is not included, this is assuming you're not going to need to build any new transmission infrastructure. Right, you're building a power plant, the line is already there. Okay, so most of the times you have to build a little bit of new transmission to get to the line. But the sort of siting is, so that is normally not that much of a cost. So now you look at how much can you produce, right, in a year. So you have a 0.8 factor, 500 megawatt. There is 8760 hours per year. So with the annual production, 3 megawatt hour. Yeah, so you're about 3 million megawatt hour. Okay, so what this shows you is actually a megawatt hour is a very small unit. So you often you see numbers. For example, people say, "Oh, this EV fleet, has equivalent of 1,000 megawatt hour of something." And that turns out to be a fraction of a plant. Okay, so a gigawatt hour over a year is a very small number for people. Okay, so there's just something to keep in mind. This seems large, so you want this is 3 terawatts. So this is essentially you have a 500 megawatt plant is a small plant. It's a medium-sized plant. So a medium-sized plant operating for a year at 80% utilization is 3 terawatt hour of power. Okay, so whenever you see this kind of news report, whenever it tells you, thousands of megawatt hours, you should not think that's a big number. You should think that's a tiny, tiny number they're talking about, okay? So what's your cost? So your cost is you take the amount you're producing, multiply by the heat you need. And you get a dollar amount, this is 41. So this is your cost, right? So this is your cost of running the plant. This is your production cost, right? So this is already there, you already built the plant. Now you're running it, this is your annual cost. So hopefully your annual revenue is a lot more than this because you have to cover this number at the end. So your annual revenue is however much you generate times the average price. Okay, so this is the revenue. So you do earn a bit more, right? You do earn actually a lot more than this number. The question you ask basically, is this difference enough to justify this costing less? Okay, right? So of course, this number has to be a lot bigger than this one. But right, so that's why when you're a generator, you need a surplus. For any market design, you need to give generator surplus. You cannot have a market where the generator's revenue is exactly equal to its production cost. Right, so we may think that's a efficient market. In those sort of settings, nobody will ever build anything. Okay, so you have this sort of, and your big cost is this is a huge cost compared to these things. Okay? So you need to take this into account. So if you're actually doing this in practice, one thing that's annoying is sort of you have units, you have this sort of imperial units versus SI units that gets converted out. In the US, there's a very strange mix of BTUs and kilowatt hours that gets mixed. In the UK, it's another mix. And in some other countries, there are other units. So one thing to pay attention to, different units. But anyways, what happens is you can now what you do is you do your investment accounting, right? So this is an extremely simple version of how to do your accounting, is to say that when you build this thing, you have a negative cash flow. Each year you're getting money going to this cash flow, right? So one thing, sort of the easiest thing to do is to just sum up this column. You basically sum up your net cash flow column, and we can sum up that. So we can sum total net cash flow. This is, so this seems to be a very large number. This is not a bad number. This is a positive number, right? So a billion, $1.6 billion basically over 30 years. This is your total cash flow. Is this a right calculation to do? At this point, do you claim that your plan is actually worthwhile building? So you're an investor, I come to you saying, assuming all these numbers are true, right? Assuming all these numbers are exactly what will happen in the future. The price doesn't change, the cost doesn't change, the utilization doesn't change in the future. I do this calculation and I show you this number. I claim you can, make quite a bit of money. Should you invest? Is this the number you look at? Think about your own money, right? So, these are very large numbers. But if you want, you can knock off the six digits out of it. And I claim, if you give me $500 right now, right? So let's pretend this is a unit. If I say you give me $500, in 30 years, I'm going to give you back 1,600. Does it make sense for you to invest? Right. So you have to compare as what happens if we just put this money in the bank, right? So if I put this money somewhere, let's say in the bank, or let's say you put this into the stock market, you just track the S&P index, do anything with this, how much money does that make? Right? So that's really what you want to compare. Okay, so it's not this month, it's not these two amount necessarily you're looking at. What you're looking at is this sort of return interest rate. That's basically what you're trying to compute. You want to say is to achieve this gain, what is the interest rate if I deposit this thing in a bank? How much interest rate does the bank have to give me for me to recover this much money? So this is a very well-known concept of time value of money. Right? So all this is saying that so a dollar now is worth more in the future. Right? So this is all the concept is saying you put in the money, you can put it somewhere, and money will make interest, right? So this is okay, so money will make some interest. So the question that we'll ask is if I put, the amount of capital money in the bank and after 30 years spits out this number, what is the annual interest? What is the equivalent interest that you get? Okay. So to do this, you basically run if you have a 30-year mortgage, you run that calculation backwards. There's very standard software that does this for you. So we're not going to bother how you do this. But what you do is you compute something called internal rate of return. Okay? So it says that if I put in, what is our number in a bank that has X% annual interest, right? So what is X that will result in that number? So that's how you're computing. So in this example, you basically, this rate comes out to be basically you have this number. So it's as if you put this much money in some investment, that'll make this return. So you're basically doing comparison that you say, if I put this in somewhere, right, is there a more profitable investment? Now I'll pay you more than 13.58 per year. So there's more for profitable investment, you go for that one. If there's not, then this is a good choice for you. Okay. Any questions for this example? Good. Right. Right. Yeah. Right. Right. Yeah. This one should be a little bit low. Yeah. So yeah. So you have a middleman cost, right? You have all that cost in there, right? So, but so it's like, you're playing stock market. There's you have to go through somebody to do that, so they take a cut. Right? But roughly, you got this kind of number. The difficulty is this is extremely sensitive to all the assumptions you're making here. Okay, the average price of the electricity, the utilization rate, the fuel cost, and all that. So in practice, is what you do is you run a lot of scenarios. Right? So you run for many, many, many scenarios. You have the different parameters. Then what you do is you sort of look at what can come out, what could come out here. Okay. So this actually leads to an optimization problem. This is, leads to scenario-based optimization. So it says based on the scenario, likely scenario you think that will happen, then right. So then there's different ways to have investments. Right? There is another way to think about this problem that's sort of becoming more common now. That happens a lot in this kind of optimization problems. So scenario-based optimization, what happens is you say these are sort of independent scenarios, all with equally likelihood. And you sort of look at the statistical outcome of it. Another way to look at this is you can look at what is the worst case outcome. So that's the alternative. You say, okay, I don't care for some scenarios. I just want to know if the worst case happens, what happens to my money, right? Is it worth it for this investment? And there, the optimization, then what you run here is you do something called robust optimization. Okay, so this is, so if you don't know what this means, this basically, instead of optimizing for a given sort of realization of all these parameters, this asks you what is the sort of the worst case in this kind of possibility, and what is the worst thing that can happen. Now, the trend in this field, in sort of really when solving this kind of problem, before is mostly you run this, and you run this for a few scenarios, then you judge. Because this is showing something that's extremely simple. To really solve this, you have to consider the network, you have to consider congestion, you have to consider what happens when other things are bidding. There's a huge optimization problem goes in here. So you can't really solve it for that many scenarios. But now both advancing sort of computer and solution techniques, you start solving a lot more. You start solving sort of a lot more scenarios on what will happen. And again, also there's alternative of looking at the worst case operation. Right? So both in generation or generator planning both in planning problem and even in operation problem, you're seeing sort of different ways to solve this. All right, so any questions on this? All right, so it's unlikely you make the final decision. It's more likely that you'll be asked to write this kind of thing. There's many people who graduate from here goes for work for companies where your job is to do this kind of planning problems. Okay, so if you work, for example, GE is trying to sell somebody generators. That's for one case how GE makes money. And then there's a team of engineers running this kind of scenarios for GE. Okay, so right, so for just some higher level ideas, what you can do is right, so you can compute your return for different utilization factors and check as the utilization factor goes down, what happens to it, and at what utilization factor you will not be okay with building this generator. Right. So let's say this line is something you'll get by putting money in the bank. Right? So I don't do anything, I can get this return. So now you have to compare the price versus utilization. You draw this kind of curves. You have to say, depending on where you are, whether you make this return or not. Okay? So you're always being judged against a baseline return that you can make some money. Questions? Okay, so this is building a generator. So you do this calculation, you look at, always at the end of the day, you convert something that's to annualized rate of return. And how much percent can you make per year? And then judge against other alternatives for that money, where that money can go. And so this is when you decide to build a generator. At the same time, as you have to make a decision that if you retire a generator or not. Right? So once you build a generator, your investment cost is gone. At that time, it doesn't matter how much money you spend investing in this generator. That money is already done. That generator is already there. You're not going to think about that, right? So you only think about retirement if you can no longer recover your operating cost. If it takes more money to run the power plant, then you don't make any money by running the power plant. So this can happen. This is happening, for example, for coal. Most of the plant retirement in the US is coal. But this is not happening all around the world. For example, you look at China. China last year built more coal power plants than any year before. Okay, so US, every coal power plant is retiring. China turns out now, if you want to build anything, you would rather build coal. Okay. So what is the difference? Can I think of? Like what kind of factor determines whether you can recover your fuel costs or not? Like what is different between, say, this power system in China, where you want to build coal, versus US, you could not pay people to build coal power plant these days. Not necessarily, no. Not in coal. Right, so again, there's two factors. Right, so one is the fuel cost. Right, so fuel cost for coal in the US is actually quite high. You don't want to buy coal, it's hard to transport, it's hard to get it to a power plant. So for example, if you look at the Burke-Gilman Trail, anybody know what that trail was supposed to do? Why do we have a trail there? This is way before any of us are alive, but whenever that trail was first constructed, that trail was actually for transporting coal to the power plant. Now it's a coal-fired power plant. The trail was where you ship coal into the power plant. Okay, so apparently I was told if you were attending this university 6 years ago, 56 years ago, what you can see sort of conveyor belts of coke into the power plant through the Burke-Gilman Trail. Right, so that's obviously no longer happening. Right, so in the US, the fuel cost doesn't make sense. The second term is the utilization. So you have to think about how often the plant gets utilized, right? You really, right? So you don't think about the market price because the market price is common to everybody. It's not specific to you. But to your plant, what you have specific to you is a fuel cost and utilization. If you keep bidding at the same amount of money, how often do you get utilized? Okay. So why is it, let's say in the US, coal is not being utilized? Let's say in China or other developing countries where coal is actually being utilized quite often. So think about the load. In the US, do we have what is our load year to year? Is it growing? Is it decreasing? Is it staying the same? The overall electric load. In the US, the load is actually going down slightly every year. In the past 5, 6 years at least. The electric load, if you look how much power is needed for the US economy, is going down. It's actually, and if, right, so the sort of the raw number is going down. If you look at something like the power per GDP, this thing is going down really, really quickly in the US. Okay, so why is it our load not increasing? Right. So the main reason is more energy efficiency. It's not like we don't have growth. The equipment we have today are hugely more efficient than whatever we had even 10, 20 years ago. The energy efficiency sort of is balancing out. But then if you look at the developing country, the load is growing. You can replace, less efficient things with more efficient things, but you're just delivering power to more people. Right? There's more people who need power. So utilization is very different in different places. So you really have to think about all these kind of things when you look at what is being built around. Okay? So the decision is basically you have to guess forward. And so you sort of guess in the future, where is the trend going? Would you be able to recover your money? Does that make sense? Okay, so, right, so this is highly dependent on where you are. Even in the US, it's highly dependent on exactly where you are in the system. The utilization and fuel cost. This can matter quite a bit. Okay. All right, so that's why if you look at across the world, it's not that one technology. It's not necessarily sort of with one technology replacing another. It's highly dependent on exactly what is happening in the system. Okay. All right, so then of course all this is again, what happens here is you have to think about the price, right? So far what we presented is you have average price. What you really have is you don't have average price. The difficulty comes from thinking about this utilization. Are you operating at the peak or are you operating on the average? So how often are you in the system? How often do you get utilized? It's not always that if you get utilized 100%, the better. So that's not always the case. For that you may have to bid below your actually operating cost for that to happen. You have to really think about if you're going to bid, how do you bid to get the most profit? And if you look at the low duration curve, again, this is for PJM. We're showing 20 years ago, but really this actually doesn't change all that much this time. So what happens is this showing you the number of hours the load has reached this level. Okay? So most of the time, the load is at least this much. For a very few amount of hours, the load is there. When we build a system, what do we think about as system operators basically only cares what happens here. We don't care past this point. All you care about is does the system survive this peak? It's not what happens in average. So the peak load is much, much, much higher than the average load. And this introduces an interesting question of when you're building a power plant, both as an investor and as a system that's trying to encourage people to build. As because the peak load is much, much higher, what happens is the total capacity is typically much higher. Okay? It's much, much higher than the load, right? So because the peak can be 2-3 times the load, we have to supply the peak, we have to be able to supply the peak. So the total capacity is 2-3 times the average load. So in fact, most generators are not on all the time. Only very few generators are on close to 100% of the time. Again, those being nuclear, hydro, and things that can do black start. Those things are on. Most generators are only operate a fraction of the time. Okay. And this creates a problem. One is if you're only operating a fraction of the time, then you have to be very careful whether you invest in this generator or not. Yeah, so what if you compute this thing wrong for even a little bit? If you don't get called, then it's very costly for you to make a wrong estimate here. So some generators are on for a small. Okay, so you're not on very often. What this also creates is competition will be limited at the peak, right? So because you don't want to build a generator that's just on at the peak, so when the peak comes, there's normally not that many generators competing in the system. So that's why you can get a price at peak that's orders of magnitude higher than the price at average times. Okay, so as a generator, what you're trying to do is, if you're only on for say 1% of the time, then your goal is to charge 100 times more the price than the generator that's on 100% of the time. Okay, that's their strategy when you're building a generator. Okay, so this competition is limited. That's why in Texas you can get $10,000 per megawatt hour as a price. That's in some sense not a bug, right? It's sort of designed into the system. If you don't have competition, then you can you have market power. That's again not illegal for that to happen. Okay? And so what you have is, if you have that kind of load, your price does something like this, right? So often your price is very low, except for some fraction of the time your price goes up. And in PJM, you're capped at $1,000 per megawatt hour. So this cap, right? So it makes sense for a consumer point of view. It's not necessarily economically the one that's most efficient. This is again the market externality you're introducing to the market. That people don't want to pay more than this. I'm going to cap you. But if you want to incentivize people to build generators, this is not a useful number to incentivize people to build generators. Okay, even if you're only on a fraction of the time, you're limited by how much money you can make, right? But ideally, in a free market, what you should be able to do, you should be able to access market power if you want, right? And, if you design a really free market with a high market power, that's a good thing for the generator. They should be able to exercise. And so this is the big debate of whether you should set this cap or not, whether there should be a cap. If so, what this cap should be. This is sort of debate to no end what this number should be. Okay? So we don't feel this is again because we're vertically integrated system. And we never see anything like this. We're not exposed to this. If you live anywhere else in the US, you'll be much more cognizant of this fact that your price can spike. This does get passed down to end customers, actually. Okay. So again, if you're the most expensive generator, right? So you're always thinking about can I recover my demand, right? So you don't want to be the marginal generator, right? So most of the time you're trying to not be the marginal generator. Or if you're the marginal generator, you're trying to be the only generator that's in the system that can supply power. Okay. So when you do this calculation, goodness, you want to avoid to being the marginal generator. And this most expensive unit actually is this only runs a few hours a year. So every system have something like this. Okay, so only runs a few hours, and every system has something like this, and then the price is very high. Very, very high price. Okay, so what the generator does is basically extremely high price. And this, what happens, this is limits competition. So what happens is if you're the most expensive generator, most of the time you're not on, but if you're on, you win, right? You basically you have all the market power to set the market. You essentially you're a monopoly at this point because every other generator has hit their limit. So once they hit their limit, you're a monopoly and you can set price to the cap. You go to the price cap, and this sort of limits the competition. So ideally, you still want some competition in the market. Okay? So this creates actually some problems for the consumers. Because what people like is people will much prefer a price curve. Let's say that's a little higher than average on average, than the price curve that goes up and down. Right. So people's preference is I want something that's steady. Uh, the average price goes from say $30 megawatt hour to 35. Most people are okay with it. Most people are not okay if the price goes from 30, let's say, down to 25, but become a lot more extreme. That is when people are not happy with your price. Okay, so but this way of generator expansion is basically creates limits competition. So what this kind of model encourage people to do is most if you're a generator, you get to squeeze out of the market if you're a peaking plant. Okay, so this may actually lower the price on average, but make it a lot more extreme. And that's not ideal from sort of a consumer point of view. Okay. Any questions about that point? So this was actually recognized after the market reform. So we did the market reform. Some years after, people realized this is not necessarily great for planning to build generators. So any solution to that? Can you think of a solution to that market reform? So let's say you want more competition, right? You want some more capacity. You don't want anything in a place where so you're willing to pay a little bit extra money, let's say on average, and you want to reduce volatility. You want more people to be around when the peak comes. Any idea what to do? Like how will you encourage people to build more plants? So this is similar to the reserve question, right? So if you have it, remember if you're a reserve, you get some money even if you don't do anything, right? So for some cases, you can get money as being on reserve. You may never get called, but you still get money. So here, what right now is a lot of systems in the US, what is introduced is now we have something called a capacity market. As you're getting paid money if you build a power plant. You don't have to sell energy. If you just build a power plant, you get some money based on the capacity you can possibly provide. And that's something introduced to solve the issue of limited competition. Yeah. So right now, So this is if you just say I invest. So if you look at the table of the amount of money you can get, your revenue will have extra column, basically just saying 500 megawatt, every megawatt you get some money, right? Regardless of whether you sell power or not. And that is a hope of dealing with the fact that not enough people are building. It can get complicated for people to build. Okay? Right, so the actual analysis of this market is quite tricky. If you do a game theoretic analysis of the market, it's very, very tricky to do this analysis. It's sort of discrete components. You have to forecast what's happening in the future. But for now, it's enough for us to understand sort of there is a capacity market. And we're subsidizing generator building, basically. We're subsidizing people to build generators that may not be cleared when you actually want power. The reason is to bring down this high price at the peak. Because there's some value of having capacity. The exact accounting for that value is something that's sort of being debated quite a bit. So if you do process economics, if you sort of do research in this area, this is one big thing people are looking at. Is how do you link the capacity to the actual operation, and what is that impact on price given how people behave? Any questions on this? Okay, so if not, let's take a 5-minute break. Then we'll come back. We'll do a very quick review of all the topics that I've done in this course. Right? So we'll look at sort of the homework I've done and think about what might happen on the final. Think back to see what we have done and what might happen on the final. Right? So with one thing we started doing in this class is looking at right, so functions for optimizing functions. Right, so given some function of x, you have to be able to find the minimum, maximum of this x. Right, you have to be able to tell which one is the maximum, which one is minimum, this kind of thing. Right, this is unconstrained optimization. Given some function, optimizing over this function. Okay? So this function could be of one variable or several variables. This is okay. This is just some basic stuff we have to do in this class. So that's one topic we covered. Second topic we covered is supply and demand. Right, so we have supply functions, we have inverse demand functions. From this, we have to be able to compute the equilibrium. Right, so this equilibrium includes Q star, the quantity, and pi star, the price, right, where we will compute these numbers based on the supply and demand information. What else might you have to do for this type of questions? Think back to this kind of question in your homework. You ask, given the two functions, we'll say compute the equilibrium. What else have you been asked to do here? Let's compute the price. What else? Based on this. Right, you're being asked to compute the surpluses or the revenues, right? So the demand surplus or the produce surplus based on these functions. Okay, so you can compute the surplus, both for the demand and producer. So this makes sense for both of them. Right, so you should know how to do this, right? So Remember, this is the area between different curves. Now integrate that area, that gives you the surplus. Okay. So one thing you don't want to do is to get the final and wait until Friday afternoon and say, oh my God, what are these things I have forgotten about? Right? So at least you want to remember what all these terms are. Okay. Right? So you're given the ability to look up this kind of concepts. But again, you don't want to look through a whole quarter of stuff in a few hours. Right? That's not what you want. Okay. And look at the surplus, right? So there could be sort of different twists around this kind of concepts, right? So one thing to check, again, that's a sanity check. These should not be negative numbers. Okay, every year somebody computes the surplus as negative. Okay, if that happens, there's something wrong with that computation. Okay, that's actually a good rule in this when you're doing the problems. The price should not be negative, surplus should not be negative, right? All the things could be zero, but should not be negative. Okay. So any questions about this concept? Yeah. Okay, so again, if your question to me is, I did this calculation, can you look at whether it's right? That's probably not a very useful question to me, right? For a final exam. I won't tell you if you just show something to me whether it's right or not. Okay, so you need to, if you have a question that's clarifying, you can ask that. But try not to ask me questions like, is this thing right? Or this number doesn't look right, can you look at this and tell me what I did wrong? Those are, again, very useful questions, okay? Okay, so just something to keep in mind what you're expected to do there. Okay, so that's sort of what we did. Then we moved on to solving system of linear equations. Okay, so this is where you can use a computer, you can plug it in and solve linear equations. In the final, you'll see equations that's sort of reasonable size, right? Equation that's sort of reasonable size. And then again, your expectation will be to solve them using a computer. Okay? So you don't have to show your work once you get to there. You do have to write out what the system is, but you don't have to show any work to get the solution. Okay, and again, it's not very important how you solve this. You can solve this whatever way you want. You don't have to explain what software you use and so on. It's okay to write the equation and directly write out the solution under the equation. Okay. So then after solving some linear equations, right? So the reason we did this is really to be able to optimize problems with equality constraints. And remember where this comes up in our context is we have a cost, we have an equality constraint, for example, the summation of the generation is equal to the load, right? So that's where it comes up. So we're solving for example, things like this, right? So we'll talk about solving this sort of the basic economic dispatch problem we have. You have equality constraint, some cost, you want to solve this, right? So what this required of solving this is, of course, you have to get the optimal solution out of this, and you have to get the multiplier or the price out of this, okay? Again, this price should be a positive number, right? So Lagrange, when you solve this thing, should be a positive number. So remember the convention for the Lagrangian, when you form it, is L minus this thing, right? So that's a convention to get a positive number out of this, right? So that will be, so your solutions, if you get the sign wrong, you get some mark deducted, right? Expected, because this has a physical interpretation of price, you need to get the sign correct. Okay, so that convention matters, right? So the sign needs to come out correctly. Yeah. So this again here, we could, give you sort of equation with problem with 5 or 6 generators. You should still be able to solve this in sort of fairly quickly, right? If you get a question like this, the expectation is you solve this question fairly quickly. You know how to do this, you know how to set up the system equations, you can just solve that, right, to get the answer. Okay. Questions here about this? Okay, good. So these are right? So what's the next thing we did is, of course, you solve this thing with inequality constraints, right? So with the equality constraints, now we're solving the same problem. So this is minimizing this, subject to, you're meeting the load. Okay, so you have inequality constraints, right? The expression here is, of course, you'll find the optimal solution. You have to be able to compute now many multipliers, right? You need to declare the multiplier associated with this equality constraint and the multipliers associated with a binding inequality constraint, okay? So here again, you have to show your work. Okay, so this is you need to show right? It's not okay to just magically guess which inequalities are type, right? So you need to go through a process to show that you can find the type inequalities. You cannot come out and say, oh, generator 1 has a type lower bound, 3 has a type upper bound, right? And solve that way. Even if that's correct, right, I need to see some work. The reason is it's not hard to find a computer program to solve this. If you Google around, you can probably learn how to solve this in 10 minutes using a computer. And so here is for you to show the steps so you understand the steps there. You're welcome to use a computer program to check that your solution is correct. That's fine. That's not required, but it's okay if you do that. But it's not okay to just directly use a computer program to solve this. Okay, so show your work. Again, all the multiplier here, should be positive, right? Should the multiplier, make sure you get the sign convention correct. Okay. Questions here? Okay, so the question will be constructed in a way such that you don't have to guess that many times, but will take you for 1 or 2 times to guess this. Okay, right, so this is the within inequality constraints. Then so now you can see this sort of class basically solving problems that gets more and more complicated. Solving optimization problems gets more and more complicated. So next we're going to solve with network constraints, right? Right, so what we'll have is, in this, we're probably the most complicated we can get is a 3-bus example where we'll have limits on the lines. You're asking to solve the problem that respects the line limit. Right? So again, here is show your work, right? You have to show how you get that line limit is binding. You cannot directly and go guess that one is binding. And so show your work. And second is read the reactants on the lines carefully. Okay, don't assume numbers for reactants. Sometimes people have a tendency to assume, oh, these are equal reactants, so let me do the problem. That's not necessarily the case, right? The problem will give you some data, the reactants, read the reactants carefully. Okay. So read it carefully. There's some buses may have only generators, some buses may have generator and loads, things like that. Okay, so read it carefully, read it, and show your work to solving this kind of problems. Okay. Questions again? Right, so if you think about the final, right, you probably see this kind of question, at least one of each. Okay, so think about how long it takes you to solve this in your homework, and think about how much time you need to allocate for this one. Okay, so we have inequality constraints. So that's normally the big questions will be this one and this one. So it'll take you a while to solve this, will take you a while to solve it, right? So these will sort of be the one of the bigger problems we have. The next we have, what you did with this homework Cornell competition. Okay, so it's sort of similar to your homework you done this week, maybe with a bit of twist on competing. Again, here you have to compute the equilibrium, right, of this Cornell computation. So this could happen. And then, of course, reserve. Okay, so reserve calculation similar to what you did last homework. Okay, so the big problems will be basically a problem like this and a problem like that. Okay, it'll take you many steps to solve. The rest of the problems are relatively short. Like for reserve, I could not really ask a complicated question. That would be way too complicated, right? So the rest will be sort of fairly simple, short answers, questions. Okay. So any questions about these? So these basically, yeah. So next homework should be due tonight. Did I not change the due date? Oh, okay. Okay. So then okay. I'll post the answer tonight. Then let's not worry about handing. Okay, I'll just post the answer. Then let's not handing in the homework. Oh, sorry. I thought I changed the due date to today. No, no, it's too late. Like some people are not here, so if I set it now and it was set Friday as the deadline, then it's not very good for people who's not here. Right? Yeah, so I'll just post a solution. I'll just post a solution. Forget about handing you that homework. I'll post a solution. Oh, I thought I changed it, but I guess I forgot. Okay, yeah. So I'll post the solutions and you can just read the solution for that homework. Yeah. Any other questions? Okay, so if not, I guess good luck and see some of you on Friday.